I'm considering using the strontium detail since it's a specific element mentioned in the discovery context. The hook needs to be 2-3 sentences, 30-45 words that create immediate tension. The phrase. Antoni Przybylski leaned over the spectrograph, the faint blue glow of the 1961 observatory screen illuminating his tired eyes. His finger traced a line on the photographic plate. Strontium, impossibly strong. Iron, usually dominant, was barely visible. The numbers didn't match anything in the textbooks. He ran the data again. The spectrum of HD 101,065, cataloged years earlier by Good, showed iron peak elements vanishing. Instead, strontium, holmium, neodymium, and others flared with unnatural intensity. Przybylski felt a chill. This star's chemistry defied the known order of the universe. The common elements were weak, the rare ones were screaming. Astronomers in the decades following wrestled with the anomaly. The star, 360 light-years away in Centaurus, was classified as an app star, a type where magnetic fields can sort elements. But this was the extreme. Lanthanides were overabundant. Iron, nickel, chromium. These should have been present, yet their spectral lines were faint, almost absent. The iron group elements were below normal, while rare earth elements were thousands of times more abundant than in the Sun. Modern studies confirm the core mystery. The star's spectrum remains dominated by elements like cerium, thorium, and uranium. Some contested claims of short-lived radioactive elements linger, but those lack consensus. The star's weak iron abundance doesn't align with its high metallicity in other elements. It's not just unusual, it's a puzzle where the chemistry shouldn't exist. Przybylski's 1961 observation stands. Not a glitch in the data, but a star writing its own rules. The slow rotator, 1.5 billion years old, sits at the edge of its life. Its magnetic field might hold the key, but no known process explains such extreme segregation. The rare earth elements are not just present, they are the star's atmosphere. The question remains, how did nature arrange this impossible chemistry? The spectrum flares with strontium and holmium, sharp as shattered glass against the dark sky. Iron lines vanish. This isn't a mistake in the data. Przybylski saw it in 1961. The star's atmosphere bleeds rare earth elements, cerium, thorium, uranium. Iron, nickel, cobalt, elements that should dominate, fade into near silence. Modern spectra confirm the anomaly. The star glows 360 light-years away in Centaurus, a silent witness to chemistry that defies known physics. Its slow spin is key. Rotating at just 3.5 kilometers per second, it holds the slowest spin rate of any hot star like this. Magnetic fields, common in these app stars, likely sort elements into layers. But this star pushes the process to extremes. Iron is weak, yet lanthanides are thousands of times more abundant than in the Sun. The magnetic field might stabilize this segregation, but no model explains why the segregation is this violent, this complete. Astronomers tested explanations. Could it be a dying star ejecting its core? But its spectrum shows no signs of heavy elements being blown away. Is it a binary companion siphoning material? No evidence of a second star exists nearby. Maybe it's a new type of nuclear process, but no known fusion mechanism could produce such specific elements. The strongest theory remains stratification, magnetic fields sorting elements as the star rotates. Yet this star's stratification is 1,000 times more extreme than any other known app star. It's not just a case of uneven mixing, it's a complete chemical rewrite. The star sits at 1.5 billion years old, near the end of its life. Its weak iron abundance clashes with the high presence of others. Metallicity for iron is -2.4, meaning less than 1% of the Sun's iron. But for thorium, it's thousands of times higher. The puzzle remains. Why does nature arrange this impossible chemistry? No known process can create this. The star writes its own rules. Its spectrum is not a whisper. It's a demand for an explanation science cannot yet give. The telescope's lens catches HD 101065 as a faint blue-white pinprick in Centaurus. Its spectrum, spread across the detector, reveals something impossible. Holmium, neodymium, thorium, and uranium lines burning brighter than the sun's iron. Iron's fingerprint is nearly erased. Astronomers peer closer, adjusting filters, checking again. The star's chemistry defies every known stellar process. It's not just unusual, it's a written contradiction in the language of stars. Magnetic stratification should explain some chemical peculiarities in app stars. But here, the iron group elements are 99% weaker than expected, while rare earths like holmium are thousands of times more abundant. The star rotates at a snail's pace, 3.5 kilometers per second, yet the separation is mathematically extreme. No known magnetic field, no stable configuration, can produce this ratio. The theory cracks under the weight of the evidence. To solve this, astronomers need years of high-resolution spectroscopy, tracking each element as the star turns. Does the holmium pulse in time with the thorium? Does iron ever flicker? The star's slow rotation period, possibly 188 years, means waiting decades for a full cycle. Current observations show no shifting patterns. Without that data, the puzzle remains unresolved. A single clear pattern could confirm stratification or prove it wrong. Right now, the spectrum holds its breath. HD 101065 sits at 1.5 billion years old, near the end of its main sequence life. Its temperature is 6,131 Kelvin, its luminosity 5.6 times the sun's, yet its iron abundance is less than 1% of solar levels. Thorium is thousands of times higher. It's a star built on impossible chemistry, written in elements that shouldn't coexist this way. The universe presents a dead end. No known physics can create this arrangement. It doesn't just challenge our models, it demands a new rule book. What does this star know that we do not?